Hi, this is my second video on the area formula, and in this video I will explain where this particular definition of Jacobian comes from. Recall that the area formula says for a Lipschitz map between Euclidean spaces, basically the n-dimensional Hausdorff measure of the image of a set can be found by integrating this Jacobian over the set A. This is quotation marked because you have to count in the multiplicity. The way we will prove this, one proof of the area formula at least, goes as follows. So you break your set A into tiny pieces, only measurable, so they don't need to be as nice as I draw them here. But on each piece, your function f is very well approximated by a linear map L. And that has to do with the derivative of f, of course. So f takes this tiny blue box into any shape, basically. It's just a Lipschitz map. But f is very nicely approximated by the linear map. And the linear map takes the set into an affine space, a hyperplane, and the image of the box is, well, a bit more predictable than the image under just a Lipschitz map. Then what turns out to be the case is that Hn of image under f is quite well approximated by the Hn of image under L. We're talking about image of the blue little tiny piece. And this approximation by exhaustion ultimately will lead to the proof of the area formula. So in order to understand even the simplest cases, we have to know what linear maps do to measurable sets. How does the measure change under mapping with a linear map? So that leads to the main theorem of today. So I state it as a theorem because I will prove some lemmas before I prove this one. If L from Rn into Rm, M is always bigger in area formula, is linear, then Hn of L of A, the image of a set, is equal to the determinant of L transpose L times the Lebesgue measure of the set you started with for any measurable A in Rn. So I cannot use Ln in the image because you are sitting in Rm and Lebesgue measure is only defined at dimension m. That's why we're using the Hausdorff measure, as the picture suggests. LTL, determinant of LTL makes sense because that becomes a square matrix after multiplying with itself. So we're going to prove this, and that of course justifies why in the area formula you define the Jacobian that way. So in order to prove this one, let's see the simpler case of one Euclidean space. If V1, V2, Vn are vectors in Rn, so same number of vectors as the dimension. Okay, so I'm revealing some of my pictures I have prepared. Then the volume, which is to us will mean just the Lebesgue measure, but because we will be talking about parallelepipeds, we use the term volume. Then the volume of the parallelepiped made by VI is the determinant of the matrix whose columns are V1, V2, and Vn. Well, I have to put absolute value because it could be negative, so technically it would be false without it. Okay, so this is a very simple recipe for how to compute volume of parallelepipeds. Just put them in columns of one matrix. That becomes an n by n matrix. Just take its determinant. The sign actually tells you if VIs are in the positive orientation or not, but that's something we don't care about in this video. So how do we prove this result? You definitely will have seen this, but usually without proof, and so it's nice to give a proof anyway. So this proof will be by induction. Okay, this is true for n equal 1, although I will encourage you to think a little bit about it. Suppose it is true for n. We need to show the following. That if V1, V2, Vn, and Vn plus 1, so we're moving into Rn plus 1. The last vector I like to give a different name. So these are n plus m vectors. If these are vectors in Rn plus 1, then again the volume of parallelepiped determined by Vnw is absolute value of the determinant of the vectors V1, Vn, and then W. Absolute value. So if I succeed in doing this, then I will have proven by induction that it holds in all dimensions. I think actually it's time for us to talk about these pictures. So this situation is as follows. So we are in Rn plus m in this picture. And we have the vectors V1, V2 is going that direction, and W is the vector here. So you want to compute the volume of this parallelepiped and prove that it's equal to that determinant. Now, the picture I would love to see is the one after that, where V1 and V2 until Vn, so I'm using like 3 dimensions for pictures, but what I imply by this picture is that the span of V1 until Vn equals, we could have degenerate case. So in all of the argument, I will ignore actually the case where these vectors are linearly dependent. In that case, the dimension drops, and then you must have 0 volume, but the determinant also is 0 because some columns are linearly dependent on others. So let's rule out that case in all of the proof. So that I can write here, this is just Rn times 0. So that means the VIs lie in the flat horizontal hyperplane of the Rn plus m. and in other words, v1 to vn have no last component. The last component is just 0. And you will soon see why I love to go from this picture to that one. But what does it take to transform from this shape to the other one? The answer is that it's through an orthogonal transformation. It's through a rotation in our n. And so the proof, so this is just some thinking. Okay, cut it out from the proof. So we want to show that this volume equals to that. So here's this simplification part. So after a rotation in Rn plus m, we shall assume this thing here, that the span of these vectors equals that. In other words, happen to this, so in other words, vi can be written as vi of 1, vin, and 0 for every I. Okay, claim. This rotation does not change the volume of the parallelepiped. This is not entirely obvious if you really just want to use definition of Lebesgue measure or HN measure. So HN measure actually is easier because by its definition, it's rotation invariant. The distances do not change after rotation. With Lebesgue measure, proving that it is invariant under rotation is not completely trivial. But anyway, I believe this is kind of intuitive, and I don't want to give a proof at this moment for this, but the transformations are rigid, so we're not squishing or stretching anything, just rigid rotations. Okay, so if you believe that claim, then the other claim I have is that the determinant of v1 v and w equals determinant of v1 tilde vn tilde w tilde, where vi tilde w tilde are the vectors after the rotation. Okay, with the volume I didn't have this concern, but with determinant, after all, determinant is defined through the arrays of the matrix. You multiply this into this cofactor and so on. So when I do this rotation, the representation of the vectors does change. So a vector like 1 and 0 may be mapped to negative 1 over root 2, positive 1 over root 2, for example. And so this, now imagine how this n plus m times n plus m matrix can change drastically after the transformation. So why is the determinant not changed basically after this change of coordinate system basically? The answer is that the change of coordinate system, so the change of coordinates is via an orthogonal matrix. What you can do is that The way you actually get from this picture to this picture is, one way of doing it is to just find any orthonormal basis like this, the new orthonormal basis, blues, and declare them as your new basis. In this basis, basically you have this picture. If you declare these blues to be your new orthonormal basis of the Euclidean space, and then the change of coordinates matrix, the change of bases, we know from linear algebra, comes from multiplying by some matrix. That matrix will be an orthogonal matrix. In fact, the exact form of that matrix will be just put into the rows of this. The orthogonal matrix will be will have rows equal to this new orthonormal basis. The elements of the new orthonormal basis. Just put them in the rows of this. So the new coordinates will be multiplication of this into the old coordinates of the vectors. So how does this prove the claim? Because a determinant of v tilde v and tilde w, this vector with columns equal to that, will be determinant of this, say, is called O, orthonormal matrix. So this will be determinant of O times the matrix with vectors v1, vn, and w. So this is 1 n plus m times n plus 1 times n plus 1 matrix, and this is another one, and the change between them is through multiplication by this O. But now this breaks up into determinant of O and determinant of v1, v, and w. But this is equal to 1 or -1 because it's an orthogonal matrix. And the proof is complete once I put the absolute value here. Remember, we only care about the absolute value of them. Okay, so the two claims together show that when I go from this picture into the next picture, nothing has changed. The determinant remains the same and the volume remains the same. So it is enough to prove the claim for this one, for this picture. But that picture makes life so much easier because, so in the new picture, my determinant of v1, so now we are writing v tildes for them, v and tilde w. So let me drop this. So let's say I have already done this transformation and renamed them back to v1 to vwn. So these are vectors according to the new picture, which means that these v1s, so this is v11, v12, v1n and 0, they have no height, they're flat, v21, v2n 0, and then this continues until you have vn1, vnn 0, and then w1, w2, wn, and wn plus 1, because w is not flat. But when you compute such a determinant, if you, let me put this absolute value, this is giving me a difficult time. If you expand the determinant with respect to last row, this will be absolute value of wn plus 1 times determinant of v11, v1n, vn1, Vn like this. By induction hypothesis, we know that this will be volume of the vectors v1, vn as seen as subsets of Rn. So in this picture, we can forget that v1, v2, and so on are lying in the larger Rn plus 1. We can just assume that they are inside Rn, which they effectively are, and then n of them together, when you compute the determinant of this columns with vi's, is equal to the n-dimensional area of that base, so the green part. So my formula so far is saying that the determinant I wanted, this determinant here, is equal to this volume times Wm plus 1. But Wm plus 1 is exactly this height. But you will remember definitely what that is equal to. That is equal to the volume of the n plus 1 dimensional parallelepiped, the base times the height. But technically, that is not completely a fact you can take for granted. So you can use here Fubini's theorem or Cavalieri's principle to deduce that this is volume produced by v1, vn, and w, end of the proof, because that completes the induction. Yeah, so maybe a little bit on this Cavalieri principle. So your shape is like this, and here is the height. Every cross section with every horizontal plane cuts out the same volume because you're moving parallel in all directions. And that is why, if you apply, say, Cavalieri's principle or Fubini's theorem, you will have from here to here this height worth of the base. And that's where this comes from. Okay, what we have shown then is that if you are in Rn and you have n vectors, the volume they determine comes from taking the determinant of a matrix with columns that are exactly those vectors. Now, how does this move us toward proving the main theorem about linear maps into larger space? The link is the following corollary. Suppose v1, vn are vectors inside Rm, a bigger Euclidean space. Then the volume of the parallelepiped determined by them equals determinant of what we call the gram matrix of v1, vn. What is the gram matrix? That will be a matrix whose arrays are just dot products of vi's and vj's. So it's symmetric because dot product is symmetric. So you just take v1 and dot product it with every other guy, and you put it in the row, first row, and then you pick v2 and multiply it with all of the others, including itself actually, and then you put it in the second row and then you keep going on. Okay. Proof. If V1, Vn were vectors in Rn, then by lemma that we just proved, this volume of V1 to Vn would be equal to the absolute value of determinant of the vector, the matrix whose columns are the vectors Vi. But then we make the following observation. So if you, this is a square matrix, n by n. If you multiply it by its transpose, well, the determinant of the transpose of a matrix equals the determinant of the matrix itself. So if you multiply it twice and you take the root, you have the same quantity. So this would be determinant of take transpose of this matrix, which let's call is V, and then multiply it with itself. This is just a simple linear algebra fact. Firstly, because determinant is multiplicative. Secondly, because determinant of transpose equals to the determinant of the original matrix. But then this is exactly, VTV is just the gram determinant of V1 to Vn, because row I times column j is just Vi Vj dot product. So this we already knew from before, and we just rewrote the expression as a new, in a new shape. But what is nice about this gram determinant is that now that you had n vectors inside Rn, this is your Rn, and here is your Rm, the full picture is Rm. If you tilt this Rn inside Rm, so you give it some rotation and you bring it up this way, and the vectors Vi get translated with it. So if we rotate, first if we embed Rn inside Rm and rotate it around, then gram determinant of V1, Vn does not change. The first remarkable thing about gram determinant is that you can form it even if your matrices are inside a larger space. Notice that this V will no longer be a square matrix if your VIs are taken from Rm. This will be just a rectangular matrix. But the gram determinant will always be a square matrix by its definition. And then there's this remark that it actually doesn't change if you rotate your lower dimensional space inside the bigger one, because the dot product doesn't change under rotations. And neither does the volume when you do this rotation. And I believe this is the end of the proof of the corollary. So, or maybe if you're not comfortable with this, do the reverse. So suppose you start here with the tilted picture. You rotate this picture. It doesn't change volume. It doesn't change the gram determinant. And now you can assume that all of your VIs are actually inside the flat horizontal piece of a copy of Rn that is lying inside Rm. Then you can ignore whatever is off this plane. So you're back to the n-dimensional n vectors chosen case. And in that case, then this is lemma, and the rest is just algebra. Okay, so that's the magical thing about gram determinants. and then the corollary is proven. So if you take fewer vectors than the full dimension, you can still talk about their volume by the use of this magical gram determinant thing. And that completes our list of tools needed to prove our theorem. So let be a parallelepiped determined by v1 to vn inside Rn. Then L of p, the image of this parallelepiped under the linear map, remember we have a linear map going Rn into Rm, is a parallelepiped determined by L of v1, L of v2, L of vn. Okay, so your parallelepiped by a linear map gets mapped to another parallelepiped, and each side vi maps to LVI, so this follows. Thus, the volume of the LP, according to our corollary, equals the gram determinant. So let's square this so that I don't have to take this huge square root. So this will be determinant of the gram determinant of LV1, LVN. This will be determinant of, so what is the gram matrix? The gram matrix will be put them in a LVI into the columns, and then transpose it and multiply with itself. So this will be LV, because this is equal to LV, transposed multiplied by LV again. And this will become determinant. Now this is just algebra. I don't know what's happening here. Geometrically, there must be an interpretation. But then you see that these together is a square matrix, n by n square matrix. This is n by n square matrix. This is n by n square matrix. So we can break them up. So this becomes determinant of LTL times determinant of VTV. But this determinant VTV is just determinant of the gram determinant, and that is volume of V1 up to Vn to the power 2, and this is determinant of LTL. So take square root, and this shows to us that the volume of LP is square root of determinant of LTL times volume of P for every parallelepiped. So the volume of the image is this number times the volume of the thing in the domain. By approximating open sets with unions of parallelepipeds. Actually, you can do this by just straight rectangles with sides parallel to the coordinate axis, but we already have a stronger result, so we prove the same for arbitrary open sets. So by same, I mean the star. And then we know that the Lebesgue measure or HN measure are Borel regular, so that measure of arbitrary set a finite measure is equal to the infimum of measures of the open sets that contain it. So from that, by Borel regularity, we get star for all measurable sets. And that ends the proof of the theorem. And now it's completely justified why the Jacobians were defined the way they were defined. There is a reference for this proof. So Kant's, I think it's with a Z, and Parks have a book called Geometric Integration Theory. So they follow basically this gram determinant argument to prove that theorem. A whole other proof of the theorem, which is more often referred to, kind of is the standard argument, is using a polar decomposition of matrices. It kind of brings in the heavy machinery from linear algebra to hide everything that we did. Basically, all these rotations that you can rotate the parallelepiped to assume that this side is that way. Things do not change under rotations, which means that you're multiplying by orthogonal matrices that do not change things. All of that is just built into the polar decomposition theorem. And the one reference for that which treats it with all the details is Evans and Gary Pitt's book. This is a super famous book among analysts and geometers alike. The name of the book is Fine Properties, Measure Theory, and Fine Properties of Functions. Let me double check this title. Yes, Measure Theory and Fine Properties of Functions. This also has treatment of Hausdorff measures, Rademacher's theorem, and of course area and Koire formulas. Since some of you have asked already in comments for references, here is one, and I'll probably do a video just particularly giving resources for Hausdorff measures. Thanks a lot. Please put in the comments any part that wasn't super clear, or if you have other suggestions for a faster or cleaner proof of this this nice linear algebra result. Anyway, we will follow up the treatment of area formula with the next video soon. Thanks a lot for watching, and have a good one.